Thank you for the invitation to Scala. Everybody, welcome to the conference. What I'm going to talk about briefly is that Scala, in fact, has turned 20 years. Who would have believed that? 20 years. It's 20 years old now. Its first public release was in 2004. And at the time, it was essentially just scratching an itch, you could say. It was an experiment to say, well, I really believe that we can combine object-oriented and functional programming, even though nobody thought that was a good idea at the time. And I also believed that it would be practical. And that's why I essentially set out to do Scala, practical, to interop with Java, work on a proven platform, the JVM. It was a successor to Pizza and Funnel. So Pizza was essentially a Java extension with some of the functional features like algebraic types and closures. And Funnel was a more academic, minimalistic, calculus-oriented language. So in this talk, I want to reflect how Scala grew up from these small beginnings. And also, I want to speculate a little bit what the next 20 years could bring. And I know that's very difficult because predictions are always hairy, in particular if they concern the future. So the first 5 years, I would label the period of innocence. We didn't really know what we were doing. We were just essentially a team at a university doing a language. We had fun adding lots of cool stuff. So things that arrived at that time, I think 2006 was semicolon inference, which everybody thought was a stupid idea because it didn't work in JavaScript. Why would it work in Scala? Then lots of type stuff. We added existential types, higher kind of types, structural types, and we added extensible pattern matching. So all this appeared in this area, and it was quite opportunistic. That was really the time where you had a new grad student, and they wanted to do something, and it got in the language. Didn't happen since, so that is sort of a theme that has sort of kept since, that's how Scala functions today. It doesn't, but in the first 5 years it was true. We could do that because we had very few users. We had a handful of users, outside users, except our own students and the students we taught in classes. So it was used as a teaching language at the time. And towards the end of that period, suddenly Twitter adopted it and everything changed. So you should know that Twitter at this time was an organization of 25 people, 25 engineers and DevOps and things like that. So they were relatively small and they weren't too happy with the previous Ruby code base. It crashed too often. So the investors forced them to go back to the JVM and they said, yeah, but we don't like Java. But there's this cool new language out there, totally unproven, but hey, we're small, we do this experiment, we pick Scala. So that's how essentially the first adoption happened, and then lots of other steps followed. So the second 5 years was essentially, we were overwhelmed by the success. We had to do something, and we had to find a footing. So it was a period of really productizing and also rapid industrial adoption. 2010, I would say, was the first stable version. It really should have been Scala 1.0 if you go by today's standards, but by some combination of circumstances, it became Scala 2.8. But that was really the first stable version that had many changes and additions to the previous one. It fixed arrays, which were sort of a curious shape-shifting things before. It added the collections that were bitrot proof. The proof that they're bitrot proof is you still have basically the same collections today. The user-facing API hasn't changed much. We added specialization and named and default arguments, and the people who did this as grad students there today in this room and are managers in their organizations. So that was a long time ago. 2010 was the first Scala days in Lausanne, and also the founding of TypeSafe, the company behind Scala that morphed into Lightbend some years later. 2012 came out Scala 2.9 with parallel collections. 2013, Scala 2.10, which had as notable additions implicit classes, string interpolations, and macros. And interestingly, that was basically it. So Scala 2 hasn't really changed much from these times. So if we look at the next 5 years, then it was mostly about consolidation and some new challenges. So the consolidation was 2.11 was essentially 2.10 with better macros, but the macros were experimental anyway. They were not really an official supported product, and more focus on stability. And 2.12 was essentially migrating to Java 8, to emit Java 8 bytecode. At the same time, new challenges arrived. So Java finally moved after 10 periods, after 10 years of being almost frozen. 2014, Java 8 arrived with Lambdas, so it became a serious competitor. And at the same time, Kotlin was in incubation, which finally arrived as 1.0 in 2016. So at this time, Scala became a language with serious challenges in its space. And for us at the EPFL, that period was finally when we finally understood what we were doing all along. We didn't really know very well before. If you look at foundations, at semantics, at things that programming language people take seriously, it was all on a bit of shaky ground, and that changed in around 2016 when we had the first papers on Dot, which is the dependent object types, which is essentially the calculus, the theory that is at the base of Scala. And we also had a paper in 2017, Simplicitly, on foundations of implicits. So that's when we finally understood what exactly should be the rules for implicit parameter passing and so on. Before, it was all sort of ad hoc. We sort of tried to find our way. And based on these foundations, there was a new undertaking for a compiler and a new language, which at the time was called Doty, which was essentially meant as a Scala-inspired implementation of these new foundations of Dot and the new implicits. So the last 5 years then were the big leap to Scala 3. So there was a transition to Scala 3. It was decided in 2018 at Scala Days Berlin that in fact Doty, our essentially new researchy language, would become Scala 3. In 2019, there was an important milestone, which was Scala 2.13, which had new collections, which were basically looking for the user-side interface very much like the old collections, but had essentially a new architecture inside, and new collections were compatible with Scala 3. So we still have the same collections between 2 and 3. In 2020, just before COVID arrived, Scala 3 was discussed and approved by the SIP committee. I remember that we had to cut short the last session because people had to rush home on their planes before there were no more planes and everything shut down. It was quite dramatic. So then, 2021, we had the first Scala 3 release. Another big thing is 2023, this Scala 3 long-term support version. And in 2024, now we have the first version beyond LTS, Scala 3.4. So Scala 3 doesn't move like Scala 2. Small versions are backwards compatible, and we have them much more rapidly. Every 4 months or so, you should expect a new minor version every 4 to 6 months, something like that. But we are flexible. We don't really have a fixed schedule for that. But for users, it shouldn't matter because everything is binary compatible and backwards compatible, except if you have a library, then your library, essentially everybody who uses your library has to be on the same version. So that's why we have an LTS that we said libraries prefer LTS 3.3. That's essentially a common basis. Everybody should have 3.3 or higher, and then you can use essentially these libraries. So where we are now, I think Scala 3 is really best in class for combining OOP and functional programming. We really nailed it this time, I think, that there's not really that much to improve on this front. And it's generally a really nice language. That's the feedback I get from everyone. And that's, of course, what I think myself, but yeah, I'm partial, of course. It has solid support by Scala Center, Virtus Lab, and Lightband. And also what we observe this year is that the migration seems to have started in earnest. Tooling is mostly acceptable now. I know there are still some gaps, but I think people are working hard to fill them, and I think by and large it's acceptable. Most libraries have migrated, or they can be used as 2.13 binaries. So sometimes if a binary doesn't use macros, then you can just use the 2.13 versions. But of course, many are still on Scala 2 because the world moves slowly, in particular the enterprise world. So to just reiterate reasons to migrate to Scala 3, it's not just a nice language. I know managers don't really value that very highly usually, but it has real semantic versionings. All versions are backwards compatible. So if you had problems in the past migrating your code base, then the promise is this is one last step. And once you do that, you're on much more solid ground than you were before. And that's done through backwards compatible Tasty. So Tasty is essentially our internal version where we represent Scala programs, where we make sure that everything is backwards compatible, through the long-term support versions for long-lived stable libraries. And we have in the language essentially flags for the source version where you can indefinitely say, well, even if the language changes and some rules changes, I want to specify my source should be, let's say, 3.3, and then the compiler will honor the 3.3 rules. So that gives you assurance that essentially the language won't essentially shift under your feet. The other reason to go to Scala 3 is I think it solves really many annoyances that are in practice very, very annoying, like tuple 22. So if you, the other day I had actually my daughter, she programmed and she hit a thing and said, well, I can't add a field to a case class anymore. I said, well, how many fields does the case class have? Well, 22. And I said, yeah, she was on Scala 2. So because then, of course, lots of things with tuples and things don't work anymore. So that's a big deal. And I think with Scala 3, we have essentially solved all these annoyances. They're no longer there. Generally, it's a more modern, clean, productive language. So what about the next 20 years? What can we say about that? Well, the first question is, will Scala still be around? 20 years is a long time, and it might be that, well, maybe there will be no more Scala. But I think, of course, it will be around because essentially a language with the adoption of Scala will live basically forever. Like COBOL is still around, Fortran is still around. So in that sense, it's still around. The other question is, will the dominant version still be 2.13? So that's a tough one. And I really do hope not, because that would essentially say Scala is around as a sort of corpse of essentially only used for legacy stuff. So I really do hope not, but well, we'll see. But I think the more important question is, independent of that, why would Scala still be relevant in 20 years? The world is changing so fast with LLMs and AI and everything. The field of programming as a whole changes. So how can we make any predictions that things are still relevant? And I think we can't, but we can at least look at essentially the current situations and try to make some analogies. So what we know is that lots of code will be generated automatically, Copilot, ChatGPT, and so on. It's really like having an army of super cheap programmers that write your code for you, right? So the programmers, they might sometimes misunderstand you, they might make mistakes occasionally, but not too often, and they come basically for free. So assume you have that army at your disposal. How would your system change? What would you change in your system? So I think if you can produce more code cheaply, then it becomes even more important to control that code. Make sure that you don't break things. Make sure that there's no security breach or no just stupid mistake that has a security implications. Make sure that the system as a whole remains understandable. We know that large software systems tend to turn into big balls of mud very quickly and that it's a constant fight. So having LLMs doesn't necessarily help us in that. So that's essentially the challenge, how to control that code. So that means that architecture, so to see ahead, to have essentially outlines what your code should look like, will become even more important. Because generally, when two parts make a product and one part becomes cheap, the other part actually becomes more important and valuable. That's a universal law, and I think it will apply here as well. So what do you need to define architecture? I think ingredients that really help, that we know help, are strong typing, expressive and flexible modules, a fine-grained control of capabilities, what different part of your systems can do, and a fine-grained modeling of context in which parts these different parts of your systems will be executed. And all these things together are used to synthesize and prove guaranteed invariants, things that hold no matter what certain parts of your code will do or not do. So I think Scala is an excellent language to define architecture, and I believe also that's sort of its reason to exist in the future. So it's very, very good, as we know today, for separating infrastructure from business logic. It's a lot of the reasons why enterprises adopt Scala is to say, well, it makes it really easy to do that. We have a business logic, we have the infra, they are different, and we can split them apart cleanly. The important elements that Scala has there to offer is that objects are modules, so we have an advanced object system that you really can use as a module system, and that's been often underappreciated because people really don't understand modules by and large. So it's one of the things that is there, is undeniably important, but people don't understand it very well. We have a very advanced and regular way to model contexts using givens. That naturally supports capabilities. Capabilities are things that you pass around, and givens makes them, and using clauses makes it very easy to do so. And we can express constraints through types and context bounds and things like that. And the good news is that Scala will be even better in the future in this role because we're working on more robust dependent typing. So who here knows what the aux pattern is and has used it already? Okay, so in the future you won't need that anymore because the aux pattern is really just a patch for a shortcoming of a good, strong dependent typing, which Scala currently is lacking in one part, and I think we know how to fix it. So that's an important part. We hope to get a better integration of modules and type classes, and I think together with these things that will help fight one of the things that I see in Scala code today, which essentially we are forced to do, which is very, very long type parameter lists. So I see code like in TAP here with 5 type parameters, in Zio there are parts with 7 type parameters, and that's quite a lot, right? And I think that comes because the alternative to use type members, which would be the modular solution, the classical modular solution, is just not good enough. The type inference doesn't work well enough for them, so we are basically forced, if we use type members, to use the aux pattern, which means we switch to parameters temporarily and then go back. Or I can understand that nowadays we would use type parameters only in order not to have to do that. But if you have better member inference, then that becomes different. And the other thing is capabilities and capture checking, which is something we're working on and which will, I believe, will have very deep implications. So if you take a step back here, then one standard model that the industry uses for security, and that nowadays is even partly supported in hardware, like Cherry, is the object capability model. So it's a standard architecture for security where you say some references are capabilities, and these are references to normal objects, to normal values, just things in your program. You can create those capabilities as you can create objects, and you can endow other objects or other code with capabilities by passing the capabilities that you have created or gotten to somebody else. So you can pass a capability to somebody else. And that's all. So basically, it just means immutable reference passing, which we do all the time, but with a capability connotation. So in particular, capabilities should not be assigned to mutable variables, like global variables. You shouldn't be allowed to do that, or mutable fields, because that gives you sort of a leakage of capabilities. So this is a very simple and easy to understand and powerful model, but there are also some problems right now which prevent it from being used more widely. I think the first problem is it's just too inexpressive and tedious to use. Passing these capabilities can get quite a chore, quite a drag to get them to essentially all code that needs them. And the other part is that I mentioned endowment in here. So endowment means you get this thing forever, right? So that's not how the real world works. In capabilities, often you have a capability only temporarily in your role. Let's say I can be a professor and I have a capability to teach courses and award PhDs, but when I retire, that capability will cease. So capabilities in real worlds are temporary. and capability invalidation with this model is basically not supported. So what people do in the capability architecture is they make the capability have internally a mutable field that you can turn off. So then you think you have the capability, but when you try to use it, they said, no, the capability has been invalidated. But that's really a bad state of affairs because it uses mutation, and the basic model is purely functional. So it uses basically a hack to get something that's not supported. So what we do is what I like to call now the scoped object capability model, where we have as key additions static and dynamic scopes. So capabilities satisfy static scoping rules. They're available when they are referenced in some outer scope. So that's quite obvious and normal when capabilities are object references because, of course, you can reference anything you see in your scope. And capabilities also have dynamic scope. So that means if they survive their creation scope, so let's say I have some code and I pass a capability to it, and the code gives me back a lambda that hangs onto the capability, a closure that keeps it, then that must be declared in the result type. So for instance, here at the very bottom of this thing, I hope you can see this. Here's some new syntax that you will use for that. So if we take iterator of A and a map method which gives you a new iterator, so iterators are evaluated lazily. So as you go through step through the second iterator, you will refer to your original iterator, and you'll also refer to the function, the map function. And if we assume that both the original iterator and the map function can retain capabilities, for instance, to have side effects or to do something, then it means that the new iterator will also retain those capabilities because indirectly it will call the function and refer to the original iterator. And we mark this by this hat, which means refers to, and then essentially a set of the capabilities that something refers to. So that's essentially the new addition that we research to add to the language. And the project we do this in is called Caprese. It's a 5-year advanced research project at EPFL, 23 to 28. And that implements scoped object capabilities. It tracks resources and effects as capabilities. It solves, interestingly and importantly, the effect polymorphism problem and also the function coloring problem, which are really the same problem. So essentially, the function coloring problem is the same as the effect polymorphism problem instantiated to async effects. It prevents resource leakage in direct style async libraries such as Ox and Gears, and it gives you a higher level, simpler foundations for things where Rust is recommended today. So I believe that Rust is a very interesting language that tries to solve some of these problems with the added constraints to say no GC, no garbage collector. And that gives them a very constrained design space where things sometimes get very awkward and hard to learn. If you drop this no GC requirement and says, yes, we want a garbage collector. Garbage collectors are good for many things, but we really want to keep essentially the resource management, the tracking of effects and more, then I think something like that, Caprese, is for you. So coming soon, we're moving forward here. We have internally compiled the complete Scala standard library with capture checking, almost completely, all collections and futures and things like that. So, and we will make that available as a tasty artifact that you can use in your code, which means you can still use the 213 library, but it will look like essentially a library that has capture annotations added. And that means you can finally use it for real in your code. You can just essentially drop this thing in as a dependency, and you can start using code that uses capture checking, which is enabled by a language import in Scala 3. And that lets you essentially then use things like iterators, and if you use iterators and do map on iterators, then the system will track what essentially you refer to. Okay, and we also will add capture checking for Gears, which is a new library supporting structured concurrency and async I/O. And Gears works perfectly without that, but with capture checking, it makes it clear what is sync async without suffering function calling problems, and the capture checking prevents resource leakage, which otherwise you would have that, for instance, you have an async context, you return a closure that still means to suspend, but the suspension points have gone away, so that's sort of like an unhandled exception that escapes a try. So these things happen not very often, and people mostly ignore them today, but some people do care about that, and capture checking will actually catch that. Okay, so what about the presence? Scala at present is a bit of a conundrum. I think on the one hand, it's a simple, delightful language without foundations, so what's not to love? But in actual implementations and applications of Scala are often very complex. So it's often that one gets into a new Scala code base and it's quite a culture shock. You don't know the idioms, you don't know the style, everything looks completely foreign and unfamiliar. So I think that's a big problem that we're having. On the one hand, Scala is really easy to pick up for kids. That's often forgotten nowadays because it has this thing of complexity, but there are things like Kojo, which is essentially a coding environment which has been developed in a school in India, and there are lots of young teenagers that learn programming with Scala, and I think Scala is actually an excellent language to learn programming because on the face of it, it's very simple, it's easy to get into, and there's essentially everything sort of makes sense. So we really try to be as simple as possible and also as friendly as possible. On the other hand, we have this steep learning curve on the job, and linked to that, there's this reputation that it's very hard to find senior Scala devs. So you say, why is it hard to find Scala devs? We have taught 800,000 subscribers with our Coursera courses. 800,000 people. Well, of course, some of them drop out, but there should still be a solid number of people who've learned Scala that way. Probably quite a few in this room have learned Scala this way. So where are they now? And I think there's this gap to say, well, you learn the Coursera courses, but we need much more. We need Scala for reactive systems or things like that, and you need to know about monads and whatnot. And the people are not taught in the courses, so that seems to be the gap between sort of the junior Scala programmers that take these courses and senior programmers that are hard to find. And I think that's a pity, and it's partly self-inflicted by insisting on libraries that are too complex. The other problem, I think, is that there are too many ways to write Scala code. So it's infamous for being too many things in one. And it's not, sometimes people say it's a kitchen sink language, right? It has something for everything, so it's worse than C++. But that's actually not true. I mean, if you look at it, a number of features in Scala, it's actually not much. If you count, depending on how you count keywords, syntax constructs, and things like that, it's smaller than Kotlin or Java. So, but still it has this reputation. So I think the part is that Scala is a very flexible language that admits many different styles of programming. So it looks like a bunch of languages in one, but it's really that underneath it has a very flexible rule that allows then the next layer to create many different styles in one. And Scala III cuts that down, for instance, the rules how you write infix methods and things like that. But for the moment, we have the problem that those idioms are not yet fully enforced. So, and we have, of course, a lot of Scala II code that also can continue to compile in Scala III because the transition to Scala III is gradual, which means that right now we do have, if you take Scala II and Scala III idioms together, we do have quite a large language for the moment. I mean, you have old style implicits and new style givens and so on. There are many things that are, you have old style Java like conditionals and new style if then else. So there are many ways to write things. So what we propose now is a new initiative to promote a uniform lean Scala style. So lean Scala should focus on simplicity, emphasis on direct style. I think we now finally have the good foundations with Loom and continuations on Scala native to use that. And it should be a good basis for learning Scala. So if you have a Scala course or things like that, and you want to say, well, what should I teach to newcomers? Then I think lean Scala would be a good point to start. So what I want to do is support that with regular blog posts with discussions of language features and style tips. So I want to sort of be a bit more outspoken what my opinions are on these things. And I also want to get to a point where we can do lean Scala linting. Ideally, we would have a compiler flag or plugin that supports lean Scala syntax. And what that syntax would be is a bit in flux right now, but I think there are certain points that make sense. One thing is it should be Scala 3 only. All old Scala 2 idioms should be dropped. So no implicit, no if if parents, no a map f. You have to write a dot map f in parents. The other more controversial thing is, should we also drop some complicated or otherwise dubious constructs? I think one should at least flag them or warn about them. If one does that, then I think one should allow exemptions using language imports. So you can override the defaults by saying, well, I know what I'm doing here. I really need this thing, so let me add a language import and make it clear that I deviate from the standard that way. So that's what we try to do, and that's the end of my talk, to leave that to the conference for a thing to discuss. So if you have ideas what we should do on this front, how to simplify Scala, what we can do to promote a more uniform Scala, then let's have a discussion. Talk to me after the conference, and I would be happy to take your input. Thank you.